Magnetic effects of electric current. In 1820, Hans Christian Ørsted, one of the leading scientists, accidentally discovered that a compass needle got deflected when an electric current passed through a metallic wire is placed nearby. This observation demonstrated the connection between electricity and magnetism. That means he played a crucial role in understanding electromagnetism. Ørsted's observation helped in the development of technologies like radio, television, and fiber optics. The unit of magnetic field strength is named as the Ørsted in his honor. In this chapter, we'll learn about 1. The shapes and directions of the magnetic fields of a bar magnet. 2. The magnetic effects of a straight, looped, and coil current carrying conductors like electromagnets. And 3. The domestic electric circuits. Magnetic fields and lines. Place a bar magnet on a cardboard and sprinkle some iron filings on it. Now, tap the cardboard gently. We can observe that the iron filings arrange in a specific pattern. Do you know the reason for it? Magnets influence the space around them, causing iron filings to feel a force. This force arranges the iron filings in a specific pattern. The area around a magnet where this force can be detected is called a magnetic field. The lines formed by the alignment of iron filings represent magnetic field lines, attraction and repulsions of a magnet. When we place a compass close to a bar magnet, the compass needle deflects. The compass needle acts like a small magnet with its ends pointing north and south. The end pointing north is called the North Pole and the end pointing south is called the South Pole. We have observed that when two magnets have the same poles facing each other, then they push apart. However, when opposite poles face each other, they attract and pull together. Drawing a magnetic field line with the help of a compass needle. Get a small compass and a bar magnet. Draw the outline of the magnet on a paper. Put the compass near the north pole of the magnet. Notice that the south pole of the compass needle points towards the north pole of the magnet. The north pole of the compass points away from the magnet's north pole. Mark the positions of both ends of the needle. Move the compass needle to a new position so that its south pole now occupies the spot where its north pole was. Repeat this step-by-step process until you reach the south pole of the magnet. Now, connect the marked points on the paper with a smooth curve. This curve represents a magnetic field line. Repeat the procedure to draw as many lines as you can. Magnetic field lines. Magnetic field has both direction and magnitude. The direction of the magnetic field is where a north pole of a compass needle points. Conventionally, magnetic field lines emerge from the north pole and merge at the south pole. Inside a magnet, field lines go from south pole to north pole. Magnetic field lines form closed curves. The closeness of field lines indicates the strength of the magnet. Means stronger fields have crowded field lines, resulting in greater force on another magnet's pole. Field lines don't cross because it would confuse the compass needle pointing in two directions at once. So far, we have studied the magnetic field of a permanent bar magnet. Now, let us study the magnetic field of a straight current-carrying conductor. Magnetic field of a straight current-carrying conductor. Let us take a current-carrying conductor, a thick, straight wire, and pass it through a plain paper. See that the paper is perpendicular to the wire. Connect the wire to a circuit and allow the current to pass through it. Now, bring a magnetic compass near the conductor. We can observe the deflection of compass needle. This indicates that the electric current flowing through the copper wire has produced a magnetic effect. Let us find out the shape of this magnetic field. Sprinkle some iron filings on the paper and tap it gently. We can observe that the iron filings get arranged in concentric circles. This is the shape of the magnetic field, and these are the magnetic field lines. But how do we know the direction of this magnetic field? Place a magnetic compass on the magnetic field lines to know the direction of the magnetic field. Relation between the direction of the current flow and the direction of the magnetic field. Arrange the conductor and circuit as shown. Place the magnetic compass below the conductor and allow the current to pass through it. When the current flows from north to south direction, the compass needle deflects towards east. Now, change the direction of current flow by changing the cell arrangement. Now the current flows from south to north and the needle deflects towards west. That means if the direction of current flow changes, the direction of magnetic field also changes. Now let us see relation between the strength of magnetic field and the amount of current flow. Arrange the conductor and circuit as shown. In this circuit, we have a rheostat to increase and decrease the current flow in the circuit and an ammeter to know the value of the current. Place a compass needle at some point, say at point P on the cardboard. There is no deflection of the compass needle. That means the magnetic field of the conductor is not extend till here. Now, increase the current by adjusting the rheostat. Now we can observe the needle in the compass deflects. Means the magnitude of the magnetic field is increased with the increase in current flow. It indicates that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. Now let's see the right hand thumb rule. The right hand thumb helps to determine the direction of magnetic fields of current carrying conductors without a magnetic compass. To know the direction of the magnetic field, point your right thumb in the direction of the current. Curl your fingers round the conductor. The direction in which your fingers curl represents the direction of the magnetic field lines around the conductor. In this way, using right hand thumb rule, we can find out the direction of the magnetic field. Magnetic field of a circular conductor. When we bend a straight wire into a circular loop and pass a current through it, the magnetic field lines around the loop form concentric circles. These circles get larger as we move away from the loop. At the center of the loop, these circles appear as straight lines. Each point along the wire contributes to these straight magnetic field lines at the center. Using the right hand rule, we can see that all sections of the wire contribute to the magnetic field lines in the same direction within the loop. We can apply right hand thumb rule to know the direction of the magnetic field. If the direction of the current flow is clockwise in the loop, then the direction of magnetic field is towards south. If the direction of current flow is anti-clockwise in the loop, then the direction of the magnetic field is towards north. We can remember this direction with this technique. If the flow is clockwise, draw two arrows like this and join them. Then you will get S, which stands for south. If the flow is anti-clockwise, draw two arrows like this and join them. Then you will get N, which stands for north. Magnetic field of a coil. When an electric current flows through a coil of wire, it creates a magnetic field around the coil. This magnetic field is stronger when there are more turns in the coil, and it becomes even stronger if the coil is wound into a tight spiral. The strength of the magnetic field depends on factors such as amount of current flowing through the coil, magnetic field due to a current in a solenoid. A coil made up of numerous circular turns of insulated copper wire closely wound in a cylindrical shape is called a solenoid. The magnetic field lines around a current-carrying solenoid are similar to the magnetic field lines of a bar magnet. Both exhibit similar behavior and appearance. In a solenoid, one end behaves like a magnetic north pole, while the other acts as a south pole. Inside the solenoid, the magnetic field lines run parallel and straight. This uniform arrangement signifies that the magnetic field strength remains consistent at all points within the solenoid. A robust magnetic field generated inside a solenoid can magnetize magnetic materials like soft iron if placed inside the coil. The resulting magnet is known as an electromagnet. Force of a current carrying conductor in a magnetic field. When an electric current flows through a conductor, it creates a magnetic field around it. This magnetic field can exert a force on a nearby magnet. Henri Marie Ampere proposed that the magnet also exerts an equal and opposite force on the current carrying conductor. To determine the direction of this force, we use Fleming's left hand rule. According to this rule, if you stretch out your left hand thumb, forefinger and middle finger perpendicular to each other, your forefinger points the direction of the magnetic field, your middle finger points the direction of the current, and your thumb then indicates the direction of the force acting on the conductor. Devices utilizing this interaction between current-carrying conductors and magnetic fields include electric motors, generators, loudspeakers, microphones, and various measuring instruments. Domestic electric circuits. Electricity is supplied to our homes through the mains. The mains consist of two wires. The live wire that is positive, usually covered in red insulation, and the neutral wire that is negative, typically insulated in black. In our country, the potential difference between the two wires is typically 220 volts. That means the voltage of electric current of our homes is 220 volts. At the meter board in the house, these wires pass through an electricity meter and a main fuse before connecting to the line wires inside the house. The line wires supply electricity to separate circuits within the house. They are divided into two circuits. One rated as 5 amps for devices such as bulbs and fans, and the other one is rated as 15 amps for high power appliances like geysers, etc. The earth wire insulated in green is connected to a metal plate that is buried near the house. Do you know the purpose of this earth wire? One of the primary purpose of this earth wire is to provide a safe path for electrical currents in case of a overload or fault. If there is a short circuit or some other malfunction that causes the metal casing of an appliance or electrical device to become live with electricity, then the earth wire provides a low resistance path for the current to flow into the ground, and it prevents the electric shock to humans and animals. The earth wire helps protect electrical equipment and appliances from damage by providing a path for excess electrical current to safely dissipate into the ground. This can help prevent damage from power surges or lightning strikes. Appliances are connected across the live and neutral wires within each separate circuit, with individual switches to control the flow of current. To ensure each appliance receives an equal potential difference, they are connected in parallel. An electrical fuse is a safety device designed to protect electrical circuits and equipment from damage caused by excessive currents or overloading. Overloading can occur due to damaged insulation or appliance faults. it results in a sudden increase in current known as short circuiting. Overloading can also result from a spike in supply voltage or by connecting too many appliances to a single socket. Now let us see how does a fuse works. Fuse consists of a thin strip or wire made of a material that melts easily, such as copper or silver, and it is enclosed in a protective casing. When the current passing through the fuse exceeds a certain level, the wire heats up and melts, then it breaks the circuit and disconnects the power supply. Overloading can also result from a spike in supply voltage or by connecting too many appliances to a single socket. So this is about the magnetic effects of electric current.